Hello, this is Schedulytics. Welcome to today's session. In today's brief video, we're taking a look at multiple linear regression. We'll demonstrate it using JASP, and as we do, we'll come to appreciate its application when it comes to research. Are you new to the Schedulytics channel? Well, Schedulytics is a YouTube channel dedicated to helping anyone appreciate basic statistical knowledge that will help one to undertake any research data analysis. We hope you will find all the videos here useful, and so we encourage you to like, subscribe, and share with everyone. Multiple linear regression. This tells how two or more independent variables predict one dependent variable. The model is basically a linear regression model having multiple predictor variables. Now, if you watch our video on simple linear regression, you will know that the difference between a simple linear regression and the multiple linear regression has to do with the number of predictor variables that are involved. Whilst in simple linear regression, we have just one predictor variable. In multiple linear regression, we have more than one predictor variable. Now, since we have more than one predictor variables, it means that we'll have an equation that looks like this, where we have the outcome variable here, and then this being the constant, the C, or the y-intercept, and then we have the variables as x1, x2, x3, and it continues until we exhaust all the variables we are using. And the B or the beta associated with them correspond to their various coefficients. Now, when we undertake a multiple linear regression, an output will come, which will have all these coefficients, and then we'll be able to derive our equation using this basic format. Now, there are several methods that are used in entering data for the model analysis. The first one is the force entry, which is called the enter. And basically, this allows us to input all the predictor variables that we have into the model, and then the model does its own modeling. And it's basically the default for most regression analysis. Now, we also have the backward entry. In the backward entry, all the predictors are initially entered, and then predictors less than a given level of significance, say 0.1, are then removed. This is repeated until all the predictors are significantly associated based on statistic methods. We also have the forward entry, where the predictors with the highest, or the predictor with the highest simple regression, which the outcome variable is entered first, and then subsequent predictors are selected based on the size or the correlation that they have with the outcome variable. This continues until statistically or significantly unique variants to the model have been included in the model. Now, the last one is the stepwise entry. The stepwise entry is quite similar to the forward entry. However, in this case, the model is constantly assessed to see whether there are any redundant predictors that could be removed. These are the main methods with which we can enter the predicted variables that we are trying to assess their correlation or their regression with the outcome variable of interest. Now, the null hypothesis that is tested for is that there is no significant prediction of the outcome variable by the predictor variables. Now, having established all this theoretical background or basis behind the multiple linear regression, we now want to go to the JASP platform and use a JASP data file to be able to explore this concept. Now, let's go to the JASP platform. Beautiful. So we are here on the JASP platform. We want to go and open a data library where we can assess the scores. Good. So we'll select this particular data sets, which we'll be using to demonstrate what we are talking about here. Great. So let's have a visual inspection of the data. So this is the nature of the data that we have. It has ID, GPA, HSM, HSS, HSE, SAT-M, SAT-V, and then I think we have here gender or sex. Yes, so when you look at the variables here, they all seems to be continuous apart from gender. These are continuous variables, so they qualify for us to use for a linear regression. Now, let's explore the data and know what it's all about. So having this section in mind, we have college success linear regression. So the description is, this data set, college success, provides high school grades, SAT scores, and grade point average of 224 university students. The variables, as I discussed, are those that we saw. Now, this simple just file demonstrates the use of linear regression. Specifically, we will examine which variable best predicts GPA. First, we will fit a model predicting GPA by high score, and then we'll fit also a model that uses both the high school scores and then the SAT scores to predict GPA. So first, we are going to look at just how the high school scores affect it, and then we'll look at how SAT scores also predicts one's GPA. So you may look at the descriptive statistics, and it gives us the mean, the standard deviation minimum for all. Since these are continuous variables, it qualifies for us to use what we have done. That is cool. Now, we want to also look at the correlation. How do these variables correlate with each other? So the correlation analysis here simply help us to see that when you look at the p-values of all of these variables, they all are less than 0.05, which is the significant level. And so exploratory analysis, correlation analysis reveal that all the variables are positively related. There's no negative Pearson correlation R. And so they are all positively related and they are significant. So we can go ahead to do our linear regression. So when you look at the linear regression, when you look at this section, you look at methods. So that is what we discussed. So they are enter, that is the forced entry. We have the backward entry, the forward, and the stepwise entry. And by default, which is also always the best method, is the forced entry, where you enter all the parameters into the covariates section here, and then it gives you the analysis or the output. Now, we want to see the output and what each of the variables mean. So here, it says that this is the linear regression. Here we are looking at how the high school scores predict GPA. And from our null hypothesis and then the model's prediction, we realize that this is 0.20 times 100 gives us 20%. So he's saying that this model against the null hypothesis explains 20% of the variance when it comes to GPA. So the high school scores is able to explain one's GPA score by 20%. That is what this R-square variable here is helping us to do. Now, when you come down, we have the coefficients or the individual ones. So this is the ANOVA, which helps us to see how each of the high school scores vary, or whether there's a difference between each of those scores. And the p-value here tells us, yes, it is significantly different across the board. But where exactly is the difference? This is where the coefficient thing here is telling us that actually, out of the 3 high school grades, only HSM is significant predictor of GPA. That is true because when we look at this table here, the p-value for the T statistic, it is only SHM that has a significant p-value. The rest all have values that are greater than 0.05. Now, it also makes sense because the VIF statistics suggest that there is no problem with the multiple collinearity, where we expect that the value should be less than 2. So basically, that is how we are able to see that actually high school score predicts 20% of the variance in GPA. Now, that is that for the high school score. Now, we intend to also add the SAT score. So we have added the SAT scores, and want to see how that one also predicts the GPA score. So we click there and we have that. So now we include also the SAT score. Specifically, we include the high school grades in the null model. And then we add the SAT scores to the model to test whether SAT scores contribute significantly to the prediction of the GPA over and above the high school grades. Now, so it means that our null hypothesis will now have the R squared value to be 0.20, but that for the alternative will be 0.21. The difference here is 1. So we will conclude that the null model is the same as we expected, blah, blah. Now, the model which we are using now, including the SAT score, is able to explain only 1% of the variance more with only the high school score. So it helps us to see that aside or holding the high school grades and adding SAT score, what is the effect of SAT scores against one's GPA scores? And it helps us to see that it's only 1%. Now we do an ANOVA to see if there's a difference across board. Yes, there is obviously a difference across board because this is significant. However, when we come to the individual ones, we realize that out of the p-values for the individual SAT scores, none of them is statistically significant. And so we can say that the table of coefficients show that there is only one significant predictor upon the addition of SAT score. That is only the high school grade in mathematics actually predicts one's GPA score. So basically, this is how we can be able to know exactly what factor contributes to what outcome. Now, when you come to the model, you'll be able to know how to check to add a variable to a model or the null model. And we said that the high grade scores were what we included in the model. And so by just checking it, we add them to the model. So that is how you can control for the factor in whatever analysis you are doing. So this is multiple linear regression. Thank you very much for watching. We encourage you to like the video. We encourage you to share with all who would benefit from this video. This is Schedulytics, and until we meet again, it's a bye.